Creation of a high-temperature plasma through merging and compression of supersonic field reversed configuration plasmoids. Number 2. Experiment. The ability of the FRC plasmoid to be translated several meters allows for the FRC formation and kinetic energy for heating to be realized outside of the burn chamber and breathing blanket. The high energy density state can then be obtained through the rapid conversion of the FRC axial kinetic energy. The experiments to be described here were instigated to examine the physics of this process. To accomplish this, a new device was constructed and is referred to as the inductive plasma accelerator. The initial configuration was equipped with an enlarged merging chamber as illustrated in Figure 2. To minimize the formation time as well as maximize the FRC acceleration, the IPA device was constructed so that a new formation methodology could be employed, which is referred to as dynamic formation. The monolysis theta pinch coil utilities for FRC formation in virtually all previous FRC experiments was replaced with a set of electrical isolated and independently triggered formation acceleration coils. In the initial setup, 5 such coils were employed and all were supplied with an initial reversed biased field 0.06 Tesla. A forward bias was applied to the end coil as well as the coils in the merging compression section for the compression experiments. The formation section was increased in radius to provide for greater initial FRC flux and energy. This was followed at smaller radius by a set of pure accelerator coils with positive bias for the addition of kinetic energy after FRC formation. The merging compression chamber was reduced to this smaller radius as well. See Figure 3 for both configurations. The formation coils were energies sequentially to both form and accelerate the FRC simultaneously by executing field reversal in this sequenced fashion. The FRC flux can be maintained throughout the entire process. The terminal FRC velocity was 210 km per second with the initial configuration and as high as 300 km per second in the final configuration with additional accelerator coils. The initial plasma was generated by an annual array of 16 small coaxial plasma guns located near the quartz vacuum tube wall and the fast formation coil. See Figure 3. This device was each inductivity isolated and pressed at high current 6 kA and produced a full ionized plasma flowing at through 2 cm per microsecond. The plasma guns were based on the magnetoplasma dynamic MPD thruster, which produces a full ionized plasma and the absence of significant neutral. Follow prior to initiation was characterized in separate experiments. The ejected plasma coil ceased to form an annular plasma as indicated by end-on framing pictures. This provided for good flux trapping on reversal as indicated by the large excluded flux signal during reversal and the formation of 5 more of late FRC for acceleration. The use of plasma guns in this manner also provided for a means to keep the merging chamber and accelerator at high vacuum. This was important as a significant neutral real density considerable affected FRC behavior that prevented both FRC merging and the establishment of an equilibrium of any significant duration as indicated by the diamagnetic signals in the compression section. In the initial experimental configuration, the FRC was dynamically formed and injected into a large chamber to study the merging process without the complication of compression and additional acceleration. The merging chamber consisted of a 1.14-meter radius quartz cylinder lined with a 0.3-meter long cylindrical thin tungsten liner. A suitable base field of 0.1 to 0.2 Tesla was embedded inside this liner to radially confine the FRC plasmas during merging, while 2 multi-turn coils provided for a small mirror field 0.2 Tesla on either end of the chamber. Any array of external flux and BZ field loops were installed under each coil, as well as an axial array of BZ probes inside the tungsten shell. From this array, the excluded flux due to the presence of the FRC was obtained and the FRC velocity, radius, length, and energy was determined. A HENE laser-based interferometer measures the cross-tube line density at the axial midplane. From this diagnostic and the magnetic measurement, the plasma density and pressure balance temperature were obtained. Deuterium plasmas were employed and a calibrated neutron detector was positioned radial outside the magnet at the chamber center to measure the diffusion neutron flux. The ratio of FRC directed velocity to thermal velocity was found to be greater than 3. The merging and conversion of the FRC kinetic energy was observed to take place on the alphabenic timescale. The distinct difference between merging and the simple passage of the FRC unopposed is clearly demonstrated in the array of excluded flux signal in the interaction chamber. As illustrated in Figure 4, the two FRCs merged as they coiled to form a single FRC indicated by the peak diamagnetism appearing and remaining at the axial midplane. It is worth noting that with merging, the excluded flux increased by a factor of at least 4 greater than observed for the transiting FRC. In a constant flux cylindrical coil, the thermal conversion of kinetic energy would be manifested by a large increase in plasma length as the equilibrium axial magnetic pressure constraint determines the FRC average beta. An increase in plasma radius indicated by the greatly increased excluded flux signal would normally only occur from a large increase in toroidal flux. This large increase in excluded flux has also been observed in some translation experiments where a single FRC expands and comes to rest to fill a large chamber, and has been attributed to the possible conversion of toroidal flux into poroidal flux. Based on the results, however, this is not likely to be the correct explanation for several reasons. Any formation included toroidal flux is oppositely directed for each of the merging FRCs and would be annihilated with merging as observed in Sulfilomag counter-helicity merging. There is a more plausible for the increased plasma radius than an increase in flux. If the equilibrium length of the FRC were to expand beyond the region over which the flux is held constant, the changing end conditions will significantly affect the average beta. In equilibrium, the plasma pressure along a field line is constant and must also be in radial pressure balance with the local external field, or B and equal BE equal BVSC per 1 minus XS to the power second. At this statistical value, an average beta condition can be derived from the Maxwell stress tensor in a manner similar to that obtained for constant axial flux, with the result where R is the ratio of the FRC separatrix in the end region to that at the midplane. If the region at the end of the FRC is maintained with a magnetic field that is greater than the external field at the FRC midplane, B bigger than BE, the FRC is forced to contract axially and expand radially. With a large increase in plasma energy from thermal conversion, the FRC must expand in radial compression. The axial field between the FRC and flux converging, conserving coil until B end. At this point, the FRC can expand axially and equation will hold. In this case, the FRC is characterized by a higher beta than given by the constant axial flux relation in equation 3. The interpretation of the IPA experimental results was greatly aided by the use of 2D resistive magnetohydrodynamic MHD calculations performed with the Mercury code. By initializing the code with the experimental magnetic move forms from the experiments, the dynamic behavior of the FRC formation, acceleration and velocity was matched by adjusting the initial flux and plasma inventory. The same large increase in exceeded flux is observed in the code on thermalization as it was in the experiments, with no change in the total poroidal flux, thus confirming the interpretation given here. There was one significant difference between the code and the observed behavior of the coiling FRCs, as can be seen In the results of the calculations shown in Figure 2, complete matching was not produced in the code, whereas it was always observed in the experiments. In the code, the FRC kinetic energy is almost completely thermalized upon collision, but the small residual rebound velocity of several kilometers per second causes immediate separation of the FRCs, prohibiting further reconnection and undoing whatever reconnection that has occurred. Magnetic reconnection is one of the central processes in plasma physics. One of the key issues in understanding magnetic reconnection is what determines the magnitude of the reconnection rate. In simple two-dimensional models as employed here, the reconnection site is characterized by a local null point of the magnetic field with field lines extending from the null, forming an X-type separatrix in resistive MHD models of reconnection. Is rate is controlled by the magnitude of the resistivity. However, modifying the resistivity in the Mercury code, even with density weighted resistivities, it was not possible to obtain complete reconnection of the Manning FRCs. This is counter to the resistivity driven reconnection model found to explain the reconnection rates observed in merging Cepheromac experiment. The observed rate in Cepheromac reconnection is far too slow to explain the rate observed in the experiments here, where the FRC is found to reconnection at alphabenic speed. In contrast to typical resistive models, numerical simulations of collisionless reconnection have demonstrated that magnetic reconnection in sufficiently thin current sheets, in which Hall effects and Wheeler dynamics become important, may occur at the fast rate that does not depend on the dissipation mechanism. The reconnection rate predicted from codes with the Hall term, as well as pure particle code, predict reconnection on timescale of 30 to 50 omega minus 1. The ion cyclotron time omega to the minus 1 at peak axial compression was 1 and 0.1 microsecond for the expansion merging and compression merging experiments respectively. Again, the reconnection timescale predicated is much too long. The likely explanation is that the reconnection is inherently three-dimensional and that the local resistibility may be highly anomalous. Work is currently underway at the University of Washington employing a 3D MHD code referred to as NIMROD, which includes both the Hall and resistive teams. Hopefully this code can shed more light on the exact mechanism at play here. The basic FRC equilibrium parameters observed during compression are displayed in Figure 5. Figure 5 FRC experimental data at the axial midplane during compression for the IPA configuration shown in Figure 2, plotted from top to bottom. The radially averaged electron density, the axial magnetic field external to the FRC, the excluded flux radius, the radially averaged total plasma temperature, and the DD fusion neutron signal detected by a scintilla-based neutron detector. Total temperature was calculated based on the radial pressure balance. During compression, it can be seen that this resulted in total temperatures of 1 kiloelectron volt or more. The overwhelmingly larger ion mass dictates that the ions received virtually all the heating from kinetic conversion of the FRC motion. The MHD calculations reflect this with ion temperatures T 850 eV after collision and compression. A strong neutron signal was detected during magnetic compression from two calibrated scintillator-based detectors manufactured by HELION technology. These detectors were employed at the axial midplane to monitor the time history of the neutron flux. The EJ410 detector employed is specifically designed for detecting fast neutrons while being nearly insensitive to gamma radiation. The detector consists of zinc sulfide phosphor embedded in a hydrogenous polymer matrix structured in a series of concentric cylinders of clear plastic to facilitate light collection. The first neutron detector is directly mounted to a photomultiplier with a time response of 0.2 microseconds. A mode Carlo N particle transport code was employed to correct for neutron passage through the quartz tube. Aluminium magnets as well as the lead shielding place around the neutron detector itself, scattering and throwing from surrounding structures accounted for about a factor of 2 reduction in neutrons detected on IPA according to the MCNP calculations, even with correction for FRC geometry, attenuation, and scattering in intervening material a much higher ion temperature, T 2 keV, was inferred. The anomalously large signal was well beyond what could be attributed to measurement. Error of the plasma density and volume. Most likely it is a result of a non-thermal ion population, but the mechanism for maintaining this over the 30 microseconds of the FRC compression time is not clear. The confinement observed for the merged and compressed FRC was better than the scaling inferred from equation 2 by roughly a factor of 2 for the conditions shown in figure 5. This scaling was based on FRCs confined in constant flux coils. Enhanced confinement has also been observed in translation experiments where the FRC is expanded into and completely fills a larger chamber. It would be tempting to attribute the improved confinement to flux generation. But as discussed, this interpretation is not warranted when the FRC is merely confined. Previous compression experiments of translate FRC into a constant flux coil did not exhibit enhanced confinement. Mere confinement provides several possible mechanisms that could lead to improved confinement. It produced a stronger magnetic nozzle at the end of the FRC, throwing the open field line plasma loss, which in turn relaxes the large radial pressure gradient across the separatrix that would suppress instabilities such as lower hybrid drift that has been calculated to produce the transport scaling observed for FRCs. The increased plasma radius and beta reduced the magnetic gradient at the null and could thus reduce the flux loss for the same plasma resistivity. The rotational instability that is always observed later in the equilibrium with FRCs formed in seats was observed in the merged FRC experiments with compression but not expansion. The rotational instability occurs when alpha, the ratio of the plasma rotation compared to the ion diamagnetic drift frequency, approaches 1 for the lead rotor profit field. It can be shown that alpha L per x to the second power the experimental results are in accord with this scaling if it is assumed that the angular momentum L acquired by the FRC is smaller for both cases. It has been shown that a significant toroidal field can stabilize this mode so that the observed spin up under compression would indicate that little toroidal field is present after merging. Thank you.